Okay, so we're going to do a quick review of yesterday. So you have 3 problems. Okay, so you have the cube root of 27, a to the 6th, b to the 9th, c to the 15th. So this is an odd root. So if you're taking an odd root, like think of the 8th root of negative, or the 3rd root of negative 8. Okay, so it's an odd root. It doesn't matter if you get a positive or negative number out, right? So that's okay that that is negative 2. So we don't need absolute values on something like that because it should be negative. But on things like the square root of negative 1 to the 4th, you would do the negative 1 to the 4th first, and that would be 1. And then you take the square root of 1, which is just 1. Okay, when you see the square root already there, it just means the positive version, or the positive number. It's not plus or minus, because it was just like a plus was already there in front of it. So your answer is just 1. So basically that means if you had negative x to the 4th and then the square root and the 4 reduce down to, oh gosh, I gave you negative x squared, which is just going to be the same as x being squared. Or you can put it in absolute values. But if I had negative x to the 6th and then the square root, see how that's negative x to the 6th, so that's and under a square root, so it's negative x to the 3rd. So if that had been a negative number, they would now still be negative, so you'd need absolute values to make sure that it's positive in the end. I don't know if I explained that very well. So think of a number here. If I had negative 2 to the 6th, so negative 2 to the 6th is 64, but then when you take the square root, you should just get 8. Okay, that's not negative 2 to the 3rd. It should be negative 2 to the 3rd in absolute values. So that's what I'm saying there. Okay, so on these examples, since I have a cube root for the first one, you don't need absolute values on it at all. It's only when you have even roots. So the answer for the first one is going to be the cube root of 27 is 3. The cube root of a to the 6th is a squared, right? A squared times itself 3 times makes a to the 6th. The cube root of b to the 9th is b to the 3rd, and c to the 15th is going to be c to the 5th. You always just divide. So you did like 6 divided by 3. Okay, so you guys all get that for number 1? Okay, so now the 4th root of 16 is 2. The 4th root of a to the 8th is a squared. The 4th root of b to the 20th is b to the 5th. And the 4th root of c to the 30th, I didn't make this come out even, did I? So 4 goes into 30 how many times? 7, so that would be 28 of the numbers. And how many would be left? Right, 2. 2 would be left, 2 out of 4. So we're going to leave 2 inside the 4th root. So that's how you would do things like that. We're going to do more like that later. Okay, then you go through and you decide if something had been negative. So let's say a was negative. If a was negative, is a squared positive? Yeah, so that's okay. We don't need absolute values around that. What about if b was negative? Is b to the 5th negative then? Yeah, we want it to be positive in the end, so we want absolute values. How about c to the 7th? Yeah, so we need absolute values. And that's it. So you could just put absolute values around both of these, like together, or around each individual one. It doesn't matter to me. Yes? Would you do what now? No, on number 1, since you were taking the cube root, like if I had the cube root of negative 8, that answer is negative in the end. So you want it to be whatever sign it was originally. Okay, like cube root of 8 gives you positive 2. Cube root of negative 8 gives you negative 2. So you don't want absolute values around this because what if b was negative? That's going to be the answer. It's going to be a negative number in the end. You see what I'm saying? It's okay that we took the cube root of a negative. Okay, and on the last one, so I have the square root of 9 is 3. Square root of x squared I read as x. Square root of y to the 6th is y to the 3rd. Square root of z to the 12th is z to the 6th. But now think if any of those numbers had been negative originally. So then x would be negative, so we want positive. Y would be negative, so we want positive. And z is positive, so it's okay, because you had z to the 6th, so it's positive anyway. Okay, so it's only when you have an even root that you're worried about this. Okay, so like I was saying, you could also write this as 3xy cubed z to the 6th. It's okay if you put them both in the absolute values. Carolyn, did you check in? Okay. All right, so next up. So section 5.6 is on radical expressions. Okay, so the product property of roots says if n is even and a and b are both non-negative, then the nth root of a times b is the nth root of a times the nth root of b. Okay, notice how I said both are non-negative. The reason I'm saying that is because of the little note below. So if I had a negative square root of 2 times negative square root of 8, that doesn't equal the square root of 16. You can't just multiply them like that. Okay, we're going to talk later on about negative roots in chapters, well, 5.9, I guess, section 5.9, we're going to talk about what a negative square root is. But that's why you need for a and b to both be non-negative in this example. Okay, so basically you can multiply individual nth roots into one big nth root. So an example would be something like the cube root of 3 times the cube root of 9 would be the cube root of 3 times 9, so 27, which then you could simplify, so the cube root of 27 is 3. Or like the square root of 2 times the square root of 8 is the square root of 16, which is 4. Okay, the quotient property, same kind of thing if you have a quotient. So let's say I had the square root of 125 over 5. You can bring that square root into both pieces, or you could just do, well, let me write it a different way. Let's say you started out with the square root of 125 over the square root of 5. You can write them as square root of 125 over 5, which we know reduces to 25. Okay, so just that would be 5. Or if you had the cube root of 27 over 8, you can bring the cube root into both pieces. So cube root of 27 over the cube root of 8, and you could get 3 over 2. So 3 over 2. Kind of ran off the page there. 3 over 2. So just do cube root of 27 over cube root of 8. All right, so in our example, it says simplify each expression. And in this section, we're going to assume that all variables are positive. So basically, you're not going to need an absolute value on the end. So on your test, there will be a definite section where I'll say something like, make sure you check to see if you had a even root originally and end up with an odd power. Then you'll need absolute values. So you'll know like when you need to put the absolute values on. So on a lot of these problems, we're just going to assume everything's positive, so we're not going to worry about the absolute value part. Okay, so the first one, so I have the third root of x to the 7th times the third root of x squared, so that's going to be x to the 7th times x squared under 1 cube root. So x to the 9th. So divide your number, so your power, by your root, so it's x to the 3rd. Okay, the next one I have the 4th root of 81 times x to the 12th. So the 4th root of 81 is 3. Well, here's what I'm doing. I'm breaking it up into 4th root of 81 times 4th root of x to the 12th, which we kind of did last time. You kind of understand that. So 4th root of 81 is 3. 4th root of x to the 12th is x to the 3rd. Okay, so if I didn't say that thing about all variables are positive, think about it. On number 2, if x was negative originally, so if I had a negative number to the 12th, it would then be positive, and then I'd take the 4th root, which is still positive. So you need a positive number at the end. But x to the third, if x was originally negative, it would be negative. So that's a situation where you would have needed the absolute values. But since I said that all variables are positive, we're ignoring that. If that makes sense. Okay, so number 3. So I have the square root of 9 times the square root of x to the 10th over the square root of 2. Okay, so it's going to be 3x to the 5th all over the square root of 2. Okay, and then number 4, I have the 4th root of each one, so 4th root of 16 times the 4th root of x to the 8th over the 4th root of 5. So I get 2x squared over the 4th root of 5. Okay, so number 1 and number 2 are simplified as far as they can possibly go. But number 3 and number 4 actually have square roots in the denominator, which we don't allow. So there's certain things in math that we just don't leave that way. So that's one thing that we don't usually do. So we usually rationalize the denominator. So that means we're going to eliminate radicals from a denominator by multiplying the numerator and denominator by a quantity that makes the radicand an exact root. So think about what rational numbers are. Rational numbers don't have square roots, right? They're nice fractions or whole numbers or integers. All right, so we don't want this to have a square root on the bottom. So what could I multiply number 3 by on the top and the bottom to get rid of that square root of 2? Yeah, Gabby?
Square root of 2.
Yeah, so you guys probably remember that from geometry because you guys had to do it a lot with 30, 60, 90 triangles and 45, 45, 90. So on the bottom, we would now just have 2. And on the top, we would have 3x to the 5th times the square root of 2. So we just leave it like that. Which, most of the time, this looks more complicated than the original, so it's like, why did we do this in the first place? But it's just something we don't do in math. We don't leave square roots in the denominator. Okay, so on number 1, down at the bottom, we have the square root of 81, x to the 5th, y to the 8th, all over 2. All right, so I'm going to have the square root of 81, so I'm going to get 9. Do I have to bring the square root into each one, or you guys see that? So it's basically going into each thing. So I'm going to have 9. How about the square root of x to the 5th? How many times does 2 go into 5? Twice. What's the remainder? 1. I heard it very quietly. So I'd have x squared on the outside and 1x left on the inside. So this was like basically a 2 there. So I said, how many times does 5, or can 5 be divided by 2? Twice. There'd be 1 left over. All right, and then I'm going to multiply by the square root of y to the 8th, which is y to the 4th. And it's going to be all over the square root of 2. So I rearrange, so I have 9x squared y to the 4th, my square root of x, all over square root of 2. So what am I going to multiply on the top and the bottom? Square root of 2, right? So that's going to make it just 2 on the bottom, so a rational number. So on the top, I'm going to have my 9x squared y to the 4th, and under my square root, I'm going to have x and 2. So I'm going to write 2x. So that's going opposite the way we've been going. So we're putting them back under the square root together. All right, all over 2. So that would be your answer. Okay, the next one, so I have the square root of y to the 8th. So it's y to the 4th over square root of x to the 7th. So think about square root of x to the 7th. How many times does 2 go into 7? Kendall? 3. So you get x cubed, and then how many x's are left under the root? 1, right? Do you guys see? So it's square root of x. Okay, so this time I'm not going to multiply by the whole denominator. I'm not going to multiply by x cubed square root of x. What's the only thing I need in order to make a rational number on the denominator? You just need that square root of x. Do you guys see that? So did you see how you do not need x cubed times square root of x? You just need square root of x. That's all. So I'm going to multiply by square root of x over the square root of x. So I get y to the fourth times square root of x all over these two square root of x's. So square root of x times square root of x, that's going to be just x. Okay, so I have x cubed times x. So I get x to the fourth, and that's your answer. Notice I'm always writing the square root part on the end, like on the far right side. I do that for a reason, because some people's square roots get a little crazy. So if you'd written the square root of x in the front and then the y to the fourth, some people's square root lines get really long, and you can't tell what's underneath the square root. So you could write it in the front if you want, but I would do like a little stopper, like it stops there. But usually when you write square roots, you put them on the far right, like I'm doing. It's normal. Okay, so the next one I have the cube root of 2 on the top, all over the cube root of 9x. So this is a hard one. Okay, so this is different than the square root. You just can't multiply by the cube root of 9x. So think about it. If I just multiplied, so don't write this down. If I just multiplied by the cube root of 9x, I would get the cube root of 81x squared. So did that help me? Can I take the cube root of 81? No. Can I take the cube root of x squared? No. So think, what do I need to multiply by on the top and the bottom? What's going to make my number a perfect cube? So I already have 9. What do I need to multiply by in order to get something I can take the cube root of? Taylor? See the wheel spinning? So I already have 9. What do I need to multiply by in order to get a perfect cube? Not square root of 9. 3. Cube root of 3, right? Do you guys see it? Because then you'd have the cube root of 27. So see how if you have 9, you need another 3 in order to make 27. So I need the cube root of 3 at least. So that's going to make the number okay. It's going to make it 27, which we can take the cube root of. What about the x part? So I have 1x. How many do I need in order to take the cube root? X what? X squared, right. Do you guys see that? So I'm going to need the cube root of 3x squared. So now the denominator becomes the cube root of 27x cubed, and the numerator is now the cube root of 6x squared. That's a cube. Okay, so the denominator, you can take the cube root of it now. That was the whole point. We wanted it to be nice and rational in the end. So what is the cube root of 27x cubed? 3x, right? You got it. So 3x is on the bottom, and the cube root of 6x squared is on the top. That's a cube root. And that's it. Okay, that was a hard one. So go back up to number 4 above. So number 4 that we had before. I have the 4th root of 5 on the bottom. How many more 5s do I need in order to take the 4th root evenly? What did you say, Gabby? 3. You're going to need 3 more. Do you guys see that? So if I multiplied by the 4th root of 5 to the 3rd power, so the 4th root of 5 to the 3rd, 5 to the 3rd is 5 times 5, so 25 times another one. So 125. So I have 125 under there. I know it's hard to see. It's like widescreen mode. All right, so I get 2 times 125. So I get 250 under my, no, not 250. That's not under root, is it? So I get 2x squared times the 4th root of 125 all over. Now I have the 4th root of 5 to the 4th down here. Do you guys see that? That's the 4th root of 5 to the 4th, which is just 5. So on the bottom you get 5. Karen, I can print these for you. I'll print them for you. Okay, so next page. Okay, so it says radical expressions can be more difficult to simplify. So in order to add or subtract, you need like radical expressions. just like terms, you guys remember like you couldn't add 2x plus 3y because you didn't have like terms, they weren't the same variables. Just like you couldn't add 2x plus 3x squared because you had x and you had x squared. Same kind of thing. So like radical expressions have the same index, so like they're both cube roots or they're both square roots, and they have the same radicand, so they have the same number under the radical sign. So decide if the following are like or unlike. So if I had the square root of 3 and cube root of 3, could you add those? No. So these are no. So not the same index. So this was a cube root and this was a square root. All right, 5 root 3 and 2 root 3. Could you add those? Yep, you could actually. 5 root 3 plus 2 root 3 would be 7 root 3. Think of the root 3 as an x. They're both x, right? 5x plus 2x. So you could combine them and get 7x. Okay, so the next one, are these like or unlike? Unlike, right? So this is no, because this one had a 5x and this one just had a 5. Okay, and the last one, can you add those? Yeah, they're the same thing under the root, and they have the same kind of root, 4th root, and then 3a was under, so yes. All right, so number 1, we're going to simplify each expression. So some of these I can take the square root of evenly. Like 2 times square root of 25 is 2 times 5, right? Square root of 25 is 5. Plus 3 root 7 plus 9 root 7 minus square root of 9 is 3. So I get 10 minus 3. So that's 7. Then I get 3 root 7 plus 9 root 7. So think of them like x's. If you had 3x plus 9x, could you add them? Yeah. You would get 12x. So this is plus 12 root 7. And that's your answer. Okay, the next one. So I have 2 cube root of 6 and 7 cube root of 6. Those are two like terms. So 2x plus 7x would be 9x, right? So this is 9 cube root of 6. And then I have negative 5 times square root of 6, and then minus square root of 6. So again, think of them like another variable, so like y. So if I had negative 5y minus y, so negative 5y minus y, what would that be? Negative 6y, right? So this is negative 6 root 6. Okay, the next one I have multiplication. I have 2 terms for each one. So it's a binomial times a binomial, so I can FOIL. So first, outer, inner, last. I'd explain what FOIL was to Henrik yesterday. Kind of hard to explain. It's like that thing that covers like casserole dishes and silver. All right. So 2 root 3 times 3. So you get 6 root 3. So that's your first terms. Outer terms. So 2 root 3 times negative root 3. So what do you get? 2 root 3 times negative root 3. What would that be? Close. Negative 2. And then what's root 3 times root 3? 3. So negative 2 times 3, so you'd get negative 6. Inner. So you get 3 root 5 times 3. So it's just 9 root 5. And then last, so 3 root 5 times negative root 3. What do you think that one's going to be? There's definitely a negative 3 out front. What about the root 5 times root 3? What's that? Right, root 15. You just combine them. So they didn't like reduce down or anything, so root 15. So I get negative 3 root 15. And that's how that one stays. That is the answer because there are no like terms. Like you have root 3, root 5, root 15. None of them are going to combine. So that's it. All right, so you guys try number 4. So try 4. All right, so the first terms you get 4 root 2 times 4 root 2. So you get 16 and then times 2, right? So you should get 32. Your outer is negative 28 root 2. Your inner is positive 28 root 2. Your last is negative 49. So that's what I was saying. The outer and inner should cancel each other out because you have the exact same terms, but with a plus and a minus in between them. Mary? So I did 4 root 2 times 4 root 2. So just the numbers multiply to be, like, since it's multiplication, you can rearrange things. Like 2 times 3 times 4 is the same as 4 times 3 times 2, and 3 times 2 times 4. All right, so you can move them around. So I get 4 times 4 is 16. And then when I have the square root of 2 times square root of 2, just that part is what? Like square root of 2 times square root of 2? It's square root of 4, which is just 2. So it's like they, some of my students say they cancel each other out, but they're not really canceling each other out. They're just becoming what it was under the root. Okay, so it's 2 times 16. So that's how I got 32. So I have 32, and then minus 49. So what do we get? Negative 17. So negative 17 is your answer. Okay, so we did addition, subtraction, multiplication. Now we're going to do division. So the last thing is division. So it says a binomial with a root, such as 3 plus root 2, can't be in the denominator either. So you can't have any square roots in the denominator. So for this kind, in order to rationalize the denominator, we multiply by what's called conjugates. So a conjugate is the exact same thing, just with the opposite sign in the middle. Okay, so that's going to be important that you know what that's called. I think on the test I've asked in the past, like something like, if I had 4 root 2, write its conjugate. So its conjugate would be 4 minus root 2. If I had 3 plus root 7, its conjugate would be 3 minus root 7. Okay, if I had 2 minus root 5, what would its conjugate be? Just change the sign in the middle. 2 plus root 5. So those are easy points, but some people forget what a conjugate is. So they miss all those points. Okay, so it's important to know what that is. So if I have, on the denominator, I have 4 plus root 3. I need to multiply by its conjugate on the top and the bottom. So I need to multiply by 4 minus root 3 on the top and the bottom. So let's look just at the denominator right now. So leave a spot for the numerator. So if I'm foiling out the denominator, I have 4 times 4 is 16. My outer is negative 4 root 3. And my inner is positive 4 root 3. And then my last is square root of 3 times negative square root of 3. So I get negative 3. That's a negative there. Okay, so the nice thing about multiplying by the conjugate, you see how it's like the difference of 2 squares? So those outer and inner things cancel. So you're left with just 13 on the bottom. So that rationalized your denominator. It left you with a rational number on the bottom. So you get just 13 on the bottom. Okay, now we need to figure out what was on top. So see how these can be a little tricky because you could have like 2 things that you need to FOIL out. So on the numerator, now you need to FOIL the top 2. Okay, so you guys go ahead and try that. So multiply out the top. See if you can do it. And then try number 2 as well. All right, so on the top of the first one, so when you FOIL, you get 2 times 4, so 8. Outer is minus 2 root 3, inner is minus 4 root 3. And then last is plus. You're going to have root 3 times root 3, so 3. So you combine, you get 11 minus 6 root 3 all over 13. So you can leave it like that. Later on when we have i's, so I haven't told you what an I is, but you would need to write it like as 11 over 13 minus 6 root 3 over 13. So you could get in the habit of writing it this way as well. So see what I did there? I just brought the 13 into both pieces of the numerator. So I broke up the fraction. So you can do that. It's basically like the opposite of getting common denominators. See how if you started with this one, they have common denominators, so you would get this one when you combine them. So it's the opposite of common denominators. Okay, the other one, so I'm going to multiply by the conjugate of the denominator. So I'm going to multiply by 4 plus root 3 on top and bottom. So that's not changing my number at all because now I'm just multiplying my fraction by 1, right? Something over itself. So it's not changing the number. All right, so on the bottom, I think many of you guys noticed you get the exact same thing as what we had before because they're just written in a different order. You had 4 plus root 3 times 4 minus root 3. Well, now I have 4 minus root 3 times 4 plus root 3. So you're still getting 13 out. So you can FOIL it out if you want, but you still get 13. On the top, you're going to have 2 times 4 is 8. And then you're going to have outer is plus 2 root 3. Inner is plus 4 root 3. Last is square root of 3 times square root of 3, so 3. So you end up with 11 plus 6 root 3 all over 13. So you can leave it like that. Or, like I said, you could bring the 13 into both pieces, so you could write it as 11 over 13 plus 6 root 3 over 13. So that way as well.